Hello, everyone. Welcome to our IEEE Future Networks webinar. You just mute this other view. Sorry about that. So we will be getting started in about 1 minute. So just hold on a little for 1 minute and we'll get started with today's webinar. We want to thank everybody for joining. Okay, just find where that
Participants are going up big.
Yep, let me just get our intro slides up and then we will get started. Sorry that there's a little bit of echo. Let me just fix that real fast. Okay, hopefully that corrected the echo. And so, all right. Hello, everybody. Thank you for joining today's Future Networks World Forum monthly webinar series. So this is our July webinar. My name is Craig Polk. I'm the Senior Program Manager at IEEE Future Networks, and I want to give a thank you to Brian Zonstecker, who is our webinar chair, who's not able to make it today, but is very instrumental in setting up all of these webinars and activities that you view. Wanted to also just mention a little bit about Future Networks, who provides these webinars to you for free. So Future Networks, we are a technical community with more than 2,000 active participants, and we're made up of 9 different societies, and we have some great events and activities, which you'll hear a little bit about more in the next slide. Our main focus is around our IEEE INGR, which is our International Network Generation Roadmap, and it brings together great thought leaders, people from academia and industry to have talks, webinars, white papers, and tutorials. A lot of the activity around Future Networks and INGR that you can take part in are some of our events which are coming up, and just wanted to mention that real quickly before we got into our webinar. First one is we do have a deadline approaching for our Future Networks World Forum. That information is on screen. So please check out the website for more details on that. And also wanted to announce our call for papers and abstracts for our CTU regional summits. So for those of you that know the program, this is our humanitarian outreach that we do for trying to really find solutions and showcase solutions for access and of the internet and trying to solve the digital divide. So without further ado, we are going to move into our webinar topic today, which is on waste figure and waste factor, new metrics for sustainable AI. And it's my pleasure to introduce Ted Rappaport, who is a professor at University of New York University. And he also has visiting professorship at Purdue and Texas A&M. And he has done great work in establishing the NYU wireless after some additional work that he did in research centers in Austin and Virginia Tech. He's a very successful entrepreneur, as well as being able to advise such great companies as Straight Path Communications. With over 100 patents, he is a licensed professional engineer and a member of the U.S. Navy Academy of Engineering and a fellow of the U.S. National Academy of Inventors, and a life member of the American Radio Relay League, and he is recognized in the Wireless History Foundation and IEEE Vehicle Technology Society Hall of Fame. So with that, I'm going to turn it over to our esteemed presenter today. So Ted is going to go ahead and share out his screen and bring you to a great discussion today. Over to you.
Thank you very much. Thank you. Thank you so much for everyone attending, and Craig for that very nice introduction. I just want to make sure my screen is visible and that you can hear me okay.
You're coming through loud and clear, and your screen is up and ready to go.
Okay, great. Well, welcome everyone to Waste Figure and Waste Factor. I'm excited about this because it's been a 15-year journey with several generations of students and now collaborators from around the world as we try to create a unit vector, a fundamental metric, which can be the base root of any source to sink communication consumption factor, a factor that can be used to understand energy efficiency and true energy consumption. I'm going to present in this talk the journey and also the mathematics, which are pretty easy, which makes me think this could become a key standard. But before I get into that, I just want to put everything in perspective in our lifetime and those that came before us and those who will come ahead of us. If you look at energy consumption on planet Earth, it wasn't until the Industrial Revolution in the 1820s that we started to see large consumption. Until the 1820s, basically the world burned wood, leaves, foliage. That's how we got our power. And it was the Industrial Revolution with Alessandro Volta, the professor in 1800, inventing the battery, and James Watt and some of the early mechanical engineers creating the steam engine, that we had this explosion in energy consumption. And so now we would use wood to burn the turbines that created electromagnetism and energy from turbines. Maxwell was following up on the early work that led to the theories in the 1860s, and wireless came along in the 1880s, 1890s. But really, before the 1820s, planet Earth had no way to distribute or consume energy other than what we found in our backyard or in the forest. Oil was drilled in 1859, Texas, and now the Middle East in the 1930s exploded with this source of oil. And you can see that the consumption per year went from about 5 terawatt hours of power, of energy, and it started to ramp exponentially as oil and natural gas started to be distributed. So going from just a couple hundred years ago at 5 terawatts per hour, we now consume close to 200,000 terawatt hours of energy each year on planet Earth. I'm going to break this down a little bit. But you can see our energy consumption just in the last 40 years has doubled, and we're now consuming 650 exajoules. Exa is 10 to the 18th. 650 exajoules per year of energy consumed. That's a lot of energy, and it's growing, as you can see, very rapidly. An exajoule is 10 to the 18th joules, which is equal to 277.8 terawatt hours. We measure energy in watts per time. And 277 terawatt hours is an exajoule, and we're using 10 to the 18th of those each year on planet Earth, and it's growing. When you break down the energy consumption around the globe, what you see is remarkable trends. You see the developed nations, Europe and the USA, having flat energy consumption. And we're going to show that in a minute, but you can see that population is pretty flat. You look at the growth of populations around the world, and you see the massive growth in population in India and Africa. Look at Africa. Africa has tripled in 40 years in population from 500 million to 1.5 billion. It's the most populous it's the most populous continent on the planet with the most rapid population growth. India is growing very rapidly. Asia Pacific is growing rapidly. China, we're not exactly sure of the population numbers. There's a lot of mystique about what really happened during COVID in China, but best reported estimates are the growth has stopped. It may have gone down, but still very populous. And you can see the US is a small population and not growing very rapidly. Japan is in a little bit of decline. The reason why I show this is I want to show you where most of the energy consumption is. It's in relatively small populated areas. And there are public policies that have been developed by the large energy consumers, namely European, Japan, and USA, have tried to curtail energy, trying to keep a focus on energy efficiency. And some of the rapidly growing nations are simply trying to get up the curve in helping their populations become more wealthy and more into the modern world. So they've been more focused on big energy consumption to try to open up policy and get development. There's been a lot of hydroelectric, natural gas expansion around the world, and you're going to see the breakdown and dependencies of different parts of the world. It's pretty fascinating. Um, when you look at the graphs at the top, you can see how over the last 40 years, you see how the Asia Pacific region and Africa really have been ramping in energy consumption, and that's where the population growths are. And that trend is going to continue. In fact, when you look at the energy consumption by region and compare that to the carbon dioxide emissions by nonpartisan, non-political reports, my students and I have done a lot of work to compile this data. What you see is the energy consumption kind of follows the public policy, where China, with this rapid population growth and rapid emergence as a superpower technology and really growing its economy rapidly, is the largest energy consumer in the world. You can see Asia Pacific is growing rapidly, yet Europe and the US have maintained relatively steady state in the amount of exajoules per year consumed. Its population is not growing, and even though greater bandwidths and greater capabilities and greater everything has expanded in 40 years that we use electrically, things have gotten more efficient. They've kept a lid on the energy consumption, even with technology advancing in all sectors in Europe and the US, as well as in Russia and Japan, you could see. But it's really the Asian part of the world that's growing so rapidly. And that corresponds, not surprisingly, directly to carbon dioxide emissions. Now, remember, an exajoule is 277 terawatt hours. So you can see China consuming about 180 exajoules per year, and US and Russia consuming around 80 to 100 exajoules per year. Now, by the way, carbon dioxide is not a bad thing in general. In fact, carbon dioxide creates this wonderful cushion. It protects us from so many things in space. It's a good thing, and it's a natural byproduct of life, carbon dioxide. The trouble is when carbon dioxide starts collecting too much, you have too much of a good thing. You have too much of a, if you will, a canopy over the Earth. And so what happens is the atmosphere, things get trapped in, and temperature rises as you have too much greenhouse gas. It's like a blanket that's too heavy to use. And so what's fascinating is when you look at the greenhouse gas emission footprint, the carbon dioxide footprint of coal and oil, you see it's about a kilogram per kilowatt hour. So 1 kilowatt hour produces about 1 kilogram, 2.2 pounds of carbon dioxide. Oil, 840 grams, just under a kilogram. So about 2 pounds of carbon dioxide for kilowatt hour. Natural gas is half of that, so it's cleaner by a half of coal. But when you look at the renewables, solar, hydropower, wind, and nuclear, which is gaining a lot of traction, as I'll show shortly, those are much less. And that includes these greenhouse gas, the carbon dioxide numbers include the cost of producing these components, the cost of producing solar. You can see they're dramatically an order of magnitude, at least almost 2 orders of magnitude lower than the fossil fuels. And this is not controversial. The fact is we have seen a very large rise in carbon dioxide. This is done by carbon dating of ice particles found at the poles of the Earth. There's ways to analyze the carbon dioxide on Earth, and we've seen a rapid increase in carbon dioxide. Now, we use the term climate change and global warming. You hear about that? A politically hotbed to use the term global warming because that implies we are warming up the globe. Climate change, though, that's not necessarily attributable to man. It's attributable to everything. So people, to be more politically correct, use the term climate change. Climates are changing because we weren't around to know what the temperatures were 100 or 200 years ago, but we can figure out the carbon dioxide. Now, correlation is not causation, so that's why we like to use the term climate change. Look at my provider at my mountain house in Virginia. I live in or various places around the East Coast, but I have a mountain house near Blacksburg, Virginia, where I started my career at Virginia Tech. And APCO, the Appalachian Power Company, which serves West Virginia and Kentucky, this is a very coal-rich region. And just like politics are local, energy is local. Coal was mined to create the power utilities in the Appalachian region of the United States. There's a lot of coal. It's easy to get to. There's rail traffic. And you can see that APCO burns, and you can get this on your power bill. I encourage everyone to look at your power bill when you get it in the mail, your energy bill. Each provider around the world generally shows its mix of fuel to produce the energy we consume as citizens. And here you can see that coal is a big part of APCO's budget for providing consumer energy. Other parts of the world near water will have hydroelectric, or if you're near the coast, you'll have large wind turbines. Solar farms are where it's very sunny. So you can see this is a big issue in figuring out what the global footprint is. And when you look at the regional share of energy consumption, you can really see how it's the local energy sources that drive a population. And you can see in America, oil is king. In fact, you can see about 35 at the bottom, 35 exajoules per year is consumed in oil, and natural gas is just behind it at about 32 exajoules per year. And you can see in China, red to the right, coal is its major source of energy, providing it's 90 exajoules coming from coal. You also see China is a leader. China is also leading in renewable and clean energy. They have almost as much clean and renewable energy consumed as in the US does natural gas. So, and you can see the different breakdown of sources used around the world. And it's pretty fascinating to see that it's the local source that's going to drive the consumption by consumers. The reason why I mention all this is this is an important slide that when I first started giving this talk, people from Asia would point out, hey, Ted, you're showing China with a big consumption footprint, but they have a much, much bigger population than America. And it's a good point. You can see that the developed countries like America and Europe consume on a per capita basis a huge amount. Look at Russia. Russia consumes per capita consumption. This is now in gigajoules, or gigajoules, as I like to say. You can see the US and Russia are the biggest consumers of natural gas, much higher than China. In fact, China, on a per capita basis, is still a big consumer of coal, but not as much as the US is in natural gas, and as well as Russia. So fascinating to look at this, that oil consumption is greatest in the US, and Japan, Russia, and Europe are also big oil consumers, which we saw has the largest greenhouse gas emission. And when you break it down by total energy comparison around the world, you can really see that the US is an outsized consumer of energy. Per capita, we're consuming 1 out of every 4 joules on planet Earth, and we're a small amount of population. You can see also Russia, huge consumer, as well as Japan. And Europe and China are about on par for consumption per citizen. And you can see Africa and India, very small energy per citizen. That's going to ramp rapidly as those economies expand. So, so what is a gigajoule? I showed you that average consumption in gigajoules here, per capita energy consumption. A gigajoule is amazing. It's easily consumed. 3 gigajoules is equal to, if you consider a 100-watt light bulb, just keep your 100-watt light bulb on for a year, and it consumes 3 gigajoules. That's a lot of power, just keeping one 100-watt light bulb always on for a year. That's 3 gigajoules. And, an average human being in different parts of the world will consume 50, 100, 1,000 gigajoules. I mean, this is a a lot of power from one single light bulb. It's really useful to keep this in perspective. If you take 10 to the ninth of these light bulbs, a billion light bulbs, you're at a gigajoule, which is 277 kilowatt hours. Okay, so we see there's haves and have-nots in energy consumption. And this has caused this huge debate amongst different parts of the world. Climate talks, you've probably heard of this. We've had 29 years of them. At COP29 in 2024, there was a pledge by developed nations to provide 300 billion annually to help the countries that are really kind of powerless, small islands in the Pacific, or developing nations that are trying to build their economies. And there was a big fervor because these countries, islands in the Pacific, wanted to be able to be compensated for this change in climate that affects their, the climate change in carbon dioxide that affects their livelihood, that affects the oceans, that affects climate in terms of variability. And they're far apart in getting restitution, but this continues. And this makes big news. And it's a problem. It's a problem for the world because the numbers, I think they sure surprised me. I hope they surprise you and make energy consumption really come to top of mind. When you're leaving the house, turn the light bulb off, turn your AC off if you don't need it, turn the heat down if you don't need it. I mean, these are big problems. And as the world expands and as countries grow, it's going to play a bigger part of the effect of our children and our grandchildren. Okay, so now let's look at more to our field, the communications field, the ICT, information, computer technology, communications technology field, telecommunications in general. Look at the energy consumption around the world. If you total this up, it's not the 650 exajoules I showed you we consume each year, because some of that 650 exajoules goes into producing goods, producing matter, producing materials. But the actual raw consumption by people and machines that people run is about 2/3 of that, 445 exajoules. And here you can see the ICT industry as of a couple years ago. And by the way, I provide all these sources. I've got a great team of undergrads and grad students that produce these slides over several years. We're constantly looking at the stuff and trying to benchmark from the politically motivated to the non-politically motivated and trying to ferret out what's real, what's fake. And it turns out with a lot of hard work, you can find pretty accurate data that corroborates across different sources. Anyway, so you can see the ICT industry is about 4% of the world's energy consumption. What's amazing is people in residences and houses consume 1 out of 5 joules on planet Earth. Roads and vehicles, people on vehicles, it's transportation consumes 1 out of 5 joules on planet Earth. Chemicals, chemical industry, making nylon, for example, for clothes, huge energy consumer, 1 out of 10 joules. But ICT is going to start growing rapidly. And you know why. It's greater bandwidth and it's greater use of computation and AI. In fact, when you look at the energy consumption of the ICT industry, you can see on the left that user devices are a little bit less than half of the total energy. Networks about 1/3. That is the infrastructure, and data centers. Data centers are about 1/4 of the energy consumption of ICT, and this is growing most rapidly. In fact, the spending of Google, Alphabet, Microsoft, and Amazon, the spending on capital investment, CapEx, capital equipment, was greater than the entire US oil and gas industry. So the consumers of energy and ICT are spending more on their equipment than the traditional consumers of energy or producers of energy, the gas and oil companies are spending to pump it. Very, very telling and not a sustainable equation. And when you think about AI, this is staggering. You look at the most rapidly adopted technologies in the history of Earth. Netflix had this incredible adoption to 1 million users. Sorry. I'm trying to move my bar here so I can see my own slides. Netflix took 3.5 years to get to 1 million subscribers. Netflix is amazing. Airbnb The vacation industry took 2.5 years to get to 1 million users. Twitter took 2 years. Facebook took 10 months. Spotify, 5 months. Instagram, 2.5 months to get to 1 million users. But ChatGPT took 5 days. 5 days to get to 1 million users. We've never seen anything like this in the future. We've never seen anything like this. And it's only the beginning, ladies and gentlemen. In fact, when you look at the production predictions and prognostications in terawatt hours, you can see that Goldman Sachs a couple years ago was predicting that AI would only be a small sliver. These are turning out to be much lower estimates. ChatGPT at 2.9 watt hours per request, per simple request, was not as efficient as Google's zero point 0.3 watt hours, but ChatGPT since gotten more efficient. They're all driving for more efficiency, but the problem is to train the models, it takes huge amounts of computation and huge amounts of power consumed. So we're looking, if you do 9 billion daily queries on, say, an AI search engine, you're at 10 terawatts hour, but we're way beyond that. We're probably close to an order of magnitude greater than that today. This is 2 years ago. So ICT is likely to become up there in the 10 to 20% energy consumption field in the next decade, I would say, and possibly even sooner. And that's why you see these companies, these over-the-top database content providers, and large companies that are housing and storing and computing and providing the infrastructure for the telecom networks, turning to nuclear power. They're already spending more money on the CapEx than the traditional providers of energy in the US. So you see this in headlines, these major over-the-top providers looking for new energy sources, nuclear. They're buying nuclear power plants. They're looking at, they're locating their data centers and their AI computational engines near dams, near natural gas pipelines. They're actually looking for major natural gas pipeline corridors around the world and placing the computational data centers there. And this is not to be unexpected. If your market is growing so rapidly and you need energy, you're going to find it. And so you see this happening all over the world, not just in America. And so you see this small nuclear industry starting to pop up in America. The idea of having neighborhood nuclear power plants to provide many terawatt hours of power, energy that can be sourced for lots of consumers in a city, and to support the computation. It's a pretty remarkable growth rate, and I hope I've alerted you to that. And now, when we drive now, and one of the questions in the chat is, what do we do as network designers? You can see that our field, the ICT field, has been interested in ICT, but we've been struggling with how to measure it. There's so many different ICT energy efficiency metrics that exist today in telecom, circuits, and in power. Let's look at wireless networks, including the radio access network. Let's look at circuits. Let's look at data centers. And let's look at AI/ML. There are no common metrics that I know of in AI/ML other than picojoule per token. But there's no definition on what's a good token and what's a bad token. I've been asking all the AI players. There's no fundamental definition. There's no unit vector on how to measure the energy. Let me give you an example. Energy efficiency in wireless. There's ETSI, there's ITU, there's 3GPP. And all of these look at energy efficiency from different landscapes. One will look at it from the network. One will look at it from the base station. One looks at it from the mobile device. One looks at it from the user scenario. And the problem is all of these are like moving deck chairs around on the Titanic. None of them have a fundamental principle on how energy goes from a source to a sink. No one can say categorically in an analytical method that everyone agrees on what true energy efficiency and energy consumption is. It's a real problem. Let me give you an example. Energy efficiency for data centers. Right now, one of the most widely used data center energy efficiency metric is PUE, power usage effectiveness. This is used by all the major infrastructure players on the internet, all the computing centers, and it's a simple definition. It's the power used by the entire system divided by the energy focused on IT. So they're trying to break out the idea of the energy consumed by the IT provisioning and auxiliary divided by the IT energy. Makes sense. Harold Free's noise factor, which I'll talk about in a little bit, is kind of like that. Total, it's like total noise divided by the noise put in at the input. Um, The problem with this definition is IT energy doesn't go further to differentiate the IT energy to move bits from one point to another, which is what a data center does. A data center basically collects information and distributes it. So it's really a communication device. So IT energy fails to break down to a finer level the amount of energy being spent to do its work versus other things that aren't communicating bits, but are still part of what they call the IT energy. See, they're getting there, but they've missed the fine detail of how much energy is spent on useful stuff that's needed from the source to sync communication versus the energy which they call IT. Auxiliary energy is stuff not used at all, like heating fans and cooling, but they haven't gone far enough. In fact, you can see that these two different data centers have exactly the same PUE, and I'm going to come down and dial in and show you how waste figure and waste factor solves this problem and shows you that one is actually 15% more energy efficient. And we're talking about so much power consumed by data centers. 1 in 4 joules in ICT is consumed, and we don't even have a proper metric for this. So look at circuits. In circuits, we have RF power amplifiers. They're the most power hungry part of a transmitter generally. And the power added efficiency is a common metric by circuit designers. It's widely adopted. There are two different definitions. The second definition came out recently, more recently, about 30 years ago. First definition was 40 years ago. So circuit designers designing their power amplifiers have this commonly used metric of power added efficiency. For low noise amplifiers, it's a totally different metric. And it relates to the noise factor. Now, noise factor is a well understood standard that everyone uses. It's a common, I call it a unit vector for noise in a cascade. And what we're proposing is the same kind of unit vector for energy consumption in a cascade. Even IEEE has its International Network Generation Roadmap looking at energy efficiency metrics. And in fact, our host, Craig Pope, has been involved with that. They're going to have a 2024 report on the web come out by this IEEE committee. It's coming out in July, and in 2025, they'll have a web-based report coming out around November. This is some of the work that the IEEE Future Networks group does. You heard them talk about the conference in Bangalore this fall. So be looking for that. But yet, here's another organization trying to define energy efficiency. But again, I claim it's moving deck chairs along the Titanic, around the sinking Titanic. We have this sinking energy consumption that we've got to get a handle on. So I've been thinking about this problem for about 2 decades. And, maybe I'm a little weird. My friends would say I'm definitely unique. But when I go on a vacation every 7 or 8 years, I like to go to the beach and I reread the fundamental papers of Weaver and Shannon and Harold Freese. Harold Freese brought us 2 fundamental theories used in all of wireless: noise figure and his path loss in free space. And Claude Shannon, working with Warren Weaver and others, brought us information theory. And I just like to reread these papers every 7 or 8 years on the beach because they're so classic. And I've been reading them all my career. And one of the things that I just love about these founders of so much of what we use now 80, 90 years later is they go to first principles. They go down to the unit vector. In fact, you can see in Shannon's famous mathematical theory of communication, he drills down to entropy, which is something that the great Austrian scientist 60 years earlier, Boltzmann had been looking at what's the basic unit of matter. It's before they discovered the electron. And he was trying to figure out how liquid and solid states change, and he came up with this term entropy, which is like the smallest common denominator of how energy changes state in molecules. And so entropy is a term that Claude Shannon gave to information theory. And what you can see is he drills down to the fundamental idea of a cell being in its phase state. This was Boltzmann's idea. It's getting down to the very basic level. And here you can see Boltzmann's famous H theorem. This is where Shannon got his idea for information theory. It wasn't until Shannon defined the smallest unit vector called a bit, log 2, binary digit, that information theory could evolve. Without that, information theory wouldn't exist. He found the basic unit vector of information, the bit, which he then derived his famous theory. And look at Harold Freese. Harold Freese also goes to basic fundamental areas. Look, they're looking at the noise of a resistor called Johnson noise from the 1920s. And here you can see they're studying the resistance, how a resistor produces thermal noise. So Freese is going down to the basic level of a passive device creating noise. And from that, he figures out using Boltzmann's constant again. Boltzmann really did a lot for Bell Labs and for our field. He goes down to the lowest level of what energy could be produced by something sitting on the shelf. And thanks to that, Harold Freese then creates noise figure and noise factor, which is defined as basically the contributed noise along a cascade. Brilliant, but simple, going back to fundamental principles. So we did the same thing with a brilliant student, James Murdoch, in 2011. We went back to the fundamental principles. He wanted to build a perpetual motion machine. I had him read those same papers that I read on vacation, and he came back pretty excited because he said, I think we could tie Shannon's theory into a fundamental approach like Harold Freese did for noise, but we could do it for expended energy, power consumption or energy consumption across any source to sink. And we worked on it hard, and we wrote this paper in 2011, conference paper. And then in 2014, this key journal paper came out where we just defined the consumption factor. Now, the math was very crude. It was cumbersome, but we had all the elements for a fundamental unit factor. He graduated, and several other students took up the mantle of trying to make this a very compact, easy to use mathematical equation. There's a lot of good results out there, but it gets hidden by all the very difficult, complex math. So the idea was simple, but the math was a little hard in 2014, but it's a great paper to go read. You have a source and you have a sink. The source communicates to the sink over on-path and off-path devices. It's the on-path devices that carry the energy, that carry the signal. That's what Harold Freese was looking at with noise. And then you have these off-path devices which support. This is kind of like the PUE and data center. The data center had the IT, remember IT, but they didn't break it down into IT signal path and IT energy off signal path. They just called it IT devices. That's why they're missing something. They didn't get granular enough. They didn't get down to the unit vector. So this is the idea. If you have a cascade of any number of devices, one device, many devices, from a source to a sink, we've developed a theory that lets you very accurately and in a standard way compute the energy efficiency. And in this 2014 paper, we looked at the energy bit per consumption, and we extended Shannon's theoretical capacity by taking bandwidth to infinity to look at the minimum energy per bit. But now it's energy per bit minimum with the reality of this cascaded energy consumption. You see, going back to this, I'm going to show you in a minute that each energy consuming component, and even a passive component on that cascade from source to sink, is contributing to the consumed energy. Some of those devices are more efficient than others, and you're able to build up a total collection of total consumed energy from any source to sink using the parameter waste figure or waste factor, just like Harold Freese did for noise. And in 2014, we showed a relay and how you could locate, determine the energy efficiency per bit in a communication system. There we used the term consumption factor. Then in 2021, Nokia wanted to figure out if you should use a repeater or a base station in the air for a high altitude platform station. They made a math error in this paper. which I'll talk about in a minute. But they came up with the overall right result that you want to use a relay and not a full base station. By the way, this applies to RIS, reflective intelligence surfaces. And then in 2024, we finally put the math together. We finally got nice compact expressions which derive from that 2014 paper that make this very easy to use and understand. And not only can you use this as a theory, you can measure it. You can measure it on the test bench, just like Harold Free's noise factor could be measured on the test bench. And here's how it works. It's very simple. We define the term W as simply the total consumed power on the path divided by the output or usable energy of the path. What a simple definition. It's such a simple definition. It's just like Harold Free's definition of noise figure being signal to noise ratio out over signal to noise, signal ratio in over signal noise ratio out. It's such a simple definition. W is basically like 1 over efficiency. It's basically 1 over the total output of a useful output signal in a cascade divided by the total path power consumed, the total power of all those components to get that signal there. Obviously, if all your signal coming out is all the power you consume, then you have a perfectly efficient W equals 1 system. And if W is very large, it means you're spending a lot of power on that whole cascade to get the usable power out of the cascade. So W greater than or equal to 1, waste factor, is a metric, a unit vector that tells all of us in any source to sink how much energy efficiency is involved. That is, how much of the total consumed energy along the path is being represented in the total desired output signal. W of 1 is perfect energy efficiency. W equal infinity is no energy efficiency. There's no signal out. So, and when you do the math, in this 2024 paper, it's elegantly shown, just like noise figure. You have this beautiful cascaded formula that all you need to know is the waste figure of each component, that is 1 over efficiency, waste figure of each component, and the gain of each component. With the efficiency and gain of each component, you now can create this universal metric that we all can use. And when you look at the mathematical equivalencies, it's remarkable. Noise factor by Harold Frees in 1944 has this cascaded recursive gain stage. Here we have waste factor with the same cascaded gain stage, but now instead of being referred to the input as Harold Frees did because he had a noisy resistor at the input, we refer it to the output. This is referred to the output because you can measure the power at the output that's useful. And by the way, Harold Frees could have done output too, and we could do input, but it makes sense to do output. Look how beautiful this is. For a source and a sink, a passive resistor has the same definition of waste factor as Harold Frees did for noise factor. The waste factor of an attenuator is equal to the loss of an attenuator, just like the noise factor of an attenuator was equal to the loss of an attenuator. And that's very revealing because it's going to be useful for passive channels. See, Harold Frees only was used for receivers. He only studied noise along a cascade in a receiver. Here we can treat total source to sink links, including the channel, because the channel is just like a resistor in terms of loss. Here's an example in a homodyne transmitter what we've done using mini circuit catalog components. And you can see now we have a metric where you can compare designs, components, and see how they work in that cascade. And you can see that the fundamental influencer of waste factor is the efficiency of the power amplifier. It's probably not surprising, intuitively you would think, but look, when you look at the RF amplifier having a 2.7 efficiency versus an 8.8% efficiency, the more efficient, that's efficiency is equal to waste factor. Think about efficiency being 1 over waste factor. So the efficiency or 1 over waste factor is better here, and you have a much lower waste factor. Follows by intuition, but the theory makes it clear. And here it doesn't matter so much if you're far away from the sink. Remember, it's just like a noise factor. The most important component was the low noise amplifier early on. Remember, F1 mattered the most. Here, it's the waste factor of the component closest to the sink. Noise factor, it's closest to the source. Waste factor, the dominant component, is closest to the sink. In this case, the RF amplifier. You can see in the baseband amplifier, it doesn't matter how efficient your baseband amplifier is, you got virtually no waste factor. Craig, I know I've got just a couple more minutes, but I'm going to use it because this is really, really important, these last few slides. Um, I mentioned to the channel. The channel can be viewed as a part of the cascade between a transmitter and receiver. And just like a resistor, the waste factor of a channel is equal to the loss of the channel. This now allows system designs, multi-user networks over large distances, small distances, repeaters, fixed wireless access, all now to be evaluated on a system level basis, a multi-user, multi-source communication networks. And what you find is you can ignore the receiver waste factor in a system analysis because the channel is generally much lossier than the receiver gain. This is a fundamental result. It's kind of like the result of Harold Freese showing that the LNA is the most important part of a receiver for noise. Here it's showing that you can ignore the receiver waste factor and the channel becomes the most important part. And just like I mentioned, there are different PAE definitions. Waste factor is a unifier for all the different definitions of PAE. You can use this simple definition of waste factor and recast all the different definitions of PAE and circuit design into one metric. And that's a waste factor metric. And now we'll go back to that data center. Well, look, this is the way the world's doing it now. Two data centers have different sizes, but they have the same power usage effectiveness. But when you break that IT energy down into the amount of power being consumed by the information sources, the ones that deliver information, and the non-information sources, when you get a little bit more granular, you get to a unit vector, and you can see the breakdown of power in a data center. Lo and behold, look what happens. You find out that the waste factor shows that you have a much more efficient data center, 1.286 versus 1.5 in the larger power consuming data center. But most of that energy is going into producing usable information that the data center sends to its customers. So they've missed it. They've missed the boat in the design of data centers because they're not getting to the fine level detail of the work needed to move a bit from a source to a sink. And mentioning bit, we've just published a paper with friends of mine at Texas A&M, Professor Sabit Ekin and his graduate students Nurullah Sevim and Mustafa Abdelhadi. It's just coming out in Nature, a new Nature related journal called Wireless Technology. It's on ArchiveX, and we show how Shannon's limit can be derived from that 2014 paper. You take the bandwidth to infinity, and you now can find a true energy per bit with the actual waste factor included. So this is vital for practical system design. And using that channel information, you can recast this minimum energy per bit in terms of the channel gains, transmitter and receiver. This is great because it shows just so vividly and acutely in a very common math that we all can use, very simple to use, that high gain receivers are going to be critical, and millimeter wave beamforming give you huge gains over the channel, and you can map that to true energy per bit in any communication system. And we studied relays, we studied transmitter efficiency, we looked at RSI placement, and we looked at fixed wireless access, because fixed wireless access is really like a relay, and it's one of the most rapidly growing part of the telecom service area. So key takeaways are: waste factor is a unified energy metric. It's a cascaded formula, just like noise figure. You're able to use Shannon's theorem, put it together to get true practical energy per bit limits. And we believe this really offers a lot of opportunity for us as a community to start getting a handle on true energy efficiency. And I hope we can move this to computing and AI. Let's get the data centers more energy efficient. And, as we go to the zeta joule era, that's 10 to the 21 joules. And we're going to be in the zeta joule era pretty soon. We're already at 650 exajoules. We're almost at a zeta joule. We've got to get a fundamental math foundation and stop moving the deck chairs on the Titanic. With that, Craig, I want to thank you and thank the audience, and it's been a real pleasure.
Awesome. Thank you so much, Ted. That was definitely a great presentation. So what we're going to do now is we're going to move into our Q&A. portion. So did see that we got a couple of these questions in here. So if we're not able to get to all of them, we apologize, and we'll definitely try to follow up with you as best as you can. And my apologies if I mangle anybody's name. I'm going to try my best. So the first one comes from Durga Prasad, who's asking about coal as the primary energy source for steel and cement industries, and how does this use contribute to greenhouse gas emissions and climate change?
Yeah, that's a good point. And you could see on the energy graphs that I showed early in the talk that that was the gross consumption, including the fuels used for those industries, right? Those fuels used for those industries. You can see roads and highways, chemicals, and construction and steel were amongst the largest energy consumers. If you want, I could go back to the slides. Should I go back to the slides or no? Um,
Yeah, yeah, if it's something quick, we could definitely go back to the slides. We have about another,
yeah, let me go back. Let me just show you where that slide was. Um,
and just as a reminder, as Ted's putting that up, if we have any questions, let's put them in the Q&A, because we may not get the questions that are in the chat. That'll just help us keep everything.
this was a good question about the here it is. So if you look at the largest, this is consumed by uh, the population, but you can see these large, these 20%, these 19%, other industries, cement. You can see iron and steel. These are big consumers. I mean, iron and steel are consuming energy. They're getting energy from multiple sources. They're generally getting it from their their power supplier, and the power supplier are these companies like APCO that are producing. So, these companies that are producing goods for the world are consuming the energy either from their own power plants or from power plants they're buying power from. And as I said, it tends to be a local source, whatever's locally there or whatever the government has driven to be popular. Look, in the US, you see this drive in the past administration to electric vehicles. You saw the electrification, and that was the goal was to try to get things more efficient and move away from greenhouse gases. Um, but it's whatever the industry, it has to consume power, and the source of power is going to continue to be driven by economics, what's cheap and what's available, and what can you transport. And you can see by this graphic clearly, coal is huge in China. Coal, energy, and you can see in the U.S oil and gas is huge. There's huge pipelines driven there. And you can see in Europe, big renewable and clean energy and big oil. So I think that answers your question. It's always going to come down to the macro sources of energy.
Okay, thanks, Ted. So we have next question is from Fisha, on what is the percentage of energy consumption due to communications network and flourishing data centers infrastructure?
Yeah, great question. So here you can see, this is as of 2023. I've got to update these slides, but you can see the ICT industry is about 4% of the global consumption after the goods are made. This is after the goods are made. So 4%. And it breaks down this way. It breaks down in 2020 at least, user devices, the consumption of energy by the 7 billion cell phones we have running today, and who knows how many billions of access points. The user devices are about 45% of that 4% global consumption. I think this is more closer to 5 or 6 now. We're probably at 5 to 6% of global consumption. It's growing very rapidly. The network, this is the network, this is the infrastructure, this is the connections between the world, the relays around the world, the internet infrastructure, networking infrastructure, the cabinets everywhere, 30%. And then data centers, this is broken down to the actual edge of the network, if you will, where the data is a quarter of the world. And I've given references for all of these sources if you want to go see, but you can see data centers becoming hyper exponential. Data centers, which is where the information is brought locally to minimize latency. Those are consuming huge amounts of power. They're being put where the energy is. They're being putting it hydroelectric dams, the over-the-top providers, the content providers, the web providers, the cloud providers are finding energy sources because this data center is growing. And we've got a bad metric. PUE is not the right metric to be handling this 24%, and that's growing. By the way, here's a little aside. We studied what the waste factor is for a typical base station and a typical cell phone. This is fascinating, and the world needs to know this, and you couldn't know it without waste factor. In fact, I'll show you. We worked with the engineers in Huawei in France and looked at their base station and base stations of other providers. I'll show you some ancillary slides. And here's an example of 4G and 5G. What we found is the waste factor of 4G base stations are about 3.5. The waste factor of 5G base stations are about 3. So they're more energy efficient in 5G than 4G. But the carriers don't realize this because the ITU has defined a waste factor, an energy efficiency metric, that's a function of the signal level or the power level being produced by a transmitter. Waste factor is beautiful because it's completely independent of any particular power level. It's an efficiency. See, a lot of the metrics being used by these different organizations are influenced by the signal level. It's not taking out the quiescent or non-useful power from the actual power delivered. So wireless network providers around the world don't realize that their 5G network's more useful than 4G. But since they're not loading the network because they think that more bandwidth leads to more power, since they're avoiding the 5G network and not loading them because all the tools used in telecom tell you 4G is better because they're carrying more bits, they're missing out on great energy efficiency by investing in 5G equipment. It's one of the reasons why the telecom world's been, I think, a little slow. I don't think the industry has had a metric to make clear to the AT&Ts or to the Oranges of the world that spend billions of dollars to a power electricity that they could be saving so much more power. Look, 3 to 3.5 is 16% roughly. You save 16% on $1 billion yearly power bill, that's $160 million. You can buy a lot more new equipment for that. That message has not been getting out because there's not a fundamental metric. That's a long answer to your question, but you can see data centers are about a quarter of it, networks about a third of it, and user devices. By the way, I meant to tell you, we found out the base station is about 3 or 3.5 by most of the manufacturers. Most cell phones are about a waste factor of 20. The waste factor of a cell phone is 20 because there's a lot of stuff in here that they know you're going to pay for when you charge your phone that the carrier doesn't have to pay for. No one has to pay for it. You pay for it.
Thanks, Ted. That's definitely important to understand where this waste factor and energy uses is coming in. There's a lot more questions on here. We're getting close to the end of the hour, so I don't think we're gonna have time to go through more of these, but we are gonna follow up with Ted, and we can try to follow up with everyone to get their questions answered. Um, so, what we're going to do now is we're going to, hear some closing thoughts from Ted, and then we're going to just let you know about our other upcoming activities in our webinar series. So, Ted, definitely want to hear some conclusions and closing remarks from you.
Yeah, well, thank you, Craig. And thank you, everyone, for taking valuable time out. I hope you'll dig into that 2014 paper, the 2024 paper, and then the one we just published with my Texas A&M colleagues who did a really nice job. We analyzed it using in a real fixed wireless and a real relay system. Look, the world is facing an energy consumption tidal wave. The dean of sustainability at Stanford calls it an energy tsunami rather than a tidal wave. Look, they're bad. And we lack a unified figure of merit for energy efficiency. And just like the Bell Labs people went down to the basic level, the bit or the noise of a resistor, we have to use fundamentals or natural laws for figures of merit. And that's what we've tried to do with waste figure. We've tried to draw on the fundamentals, a unit vector, if you will, to create a unifying figure of merit. And if we can start using this in every source to sink communication as a figure of merit, it might become like the waste figure, like the noise figure, where on every receiver you see a noise figure. On every receiver, every cell phone, every police radio, there's a noise figure. You know what the noise figure of that receiver is. We need that for every source to sink communication. But this is just the tip of the iceberg of what we need in ICT. We need to find similar metrics for computational energy. The computational energy of serial or parallel threaded computing, AI computing. We need a unit vector. Now, Landauer, in a classic 1960s paper, 1960s at IBM, came up with, there's a paper called Computing is Physical. I've got my students reading that. If we can get noise figure as a standard, we can get waste figure as a standard. And if we can get waste figures as a standard, we can get the computing industry to start looking at a fundamental energy use of computing so we can compare AI hardware and software architectures. That doesn't exist. And it's a huge problem. Those are my closing thoughts, Craig.
Well, thanks so much, Ted. Again, thank you for your time. And what we want to do now is just remind people of some upcoming activities that our technical community is doing. One is for our Future Networks World Forum, as well as our C2 regional summits. Please check out those websites for those upcoming deadlines, as well as registration that's opening soon. And on our webinar series, we have a couple more. We actually have a couple more this week, tomorrow as well as Friday, and then we already have 2 scheduled for August, so all of those registrations are open. And to just kind of keep up with all of these great activities that we do, from webinars to e-learning to events, the easiest way is to join our mailing list, to join Future Networks in our interest form. So you can go ahead and scan that, or just join on the link that's over on the right hand side. And with that, I definitely want to thank Ted Rappaport today for joining our Future Networks webinar talk, and for everyone who took time out of their day to hear about this important topic. And we look forward to having you at a future webinar or a future event, and hopefully we'll see you in person at some of our activities that are coming up in the next couple months. So thanks, everybody. Have a great day.
And Craig, thank you. Thanks to IEEE Future Networks for doing this. And I'll leave you with one final thought. Someone asked, what's the definition of waste figure? It's so simple. This is simple is good. Waste figure or waste factor is simply, it's the power totally consumed divided by the power that gets out. If all your consumed power gets out, W is 1. W is greater than 1 if you're spending more power to get the signal out than what comes out. How's that for simplicity?
That's it. Keep it simple is always the best way, right? And
Yeah,
it'll help everybody unify across the world, and we'll better humanity through this. So
there
thanks,
you go.
thanks
Thanks, Craig.
everybody, and you have
Take
all.
care.
Hey, bye.
Bye.